Hello, everybody, and welcome back. Let's continue our discussion about interfaces by now discussing the difference between an abstract data type and a data structure, and then how those fit into interfaces. I'm just going to get my main set up here as I usually do. We're going to talk about blueprints versus building, and that being the difference between an abstract data type, or ADT, and a data structure. Today, we'll make that difference more concrete using interfaces. And let's start with an example. Let's start with a stack. When we're talking about a stack, we're talking about a stack like a stack of pancakes. And that's where we are going to start this conversation. A stack data structure, or rather abstract data structure, is defined using a few different functions. The functions are push, pop, sometimes an is a size, although not always, and an is empty. So those are our methods that we're talking about. A stack is exactly like a stack of pancakes or the runtime stack that we talk about all the time, like with recursion, where we can really only deal with whatever's on the top. We push new data points on and we pop them off. This is known as the last in, first out structure, or you might see it defined as LIFO. So let's jump in. An abstract data type, or ADT, is the description of a behavior. It lists the operations that you can perform and what they're supposed to do. It does not describe how the data is being stored, only what you can do with it. In Java, we can represent this ADT, or this idea of an ADT, with an interface. Let's see it. Interface. Let's talk about maybe a string stack. When we're dealing with an interface, we do things like defining our methods, all listed one after another. Let's start with push string item, and this will push an item onto the stack. We can also pop an item. Pop. And this will remove an item from the stack. Remove an item from the top of the stack, we should probably say. Oh, I forgot one other common function here, like peek is another one, where you can look at the top but not remove it. Remove and return an item from the top of the stack. We also have peek, which is return but not remove the item from the top of the stack. And we can do a Boolean is empty, as well as a size. So we're going to define these 5 different functions here in this interface. This is an interface of a stack abstract data type for, of course, string values. We can add something to the top, remove something from the top and look at it, look at the top without removing it, tell us if there's any items left, as well as, if we're interested, talk about how many items are on the stack at a given time. You'll notice that there's no mention of arrays, there's no mention of nodes, there's no mention of the memory layout, just the operations and their types. So now let's go ahead and implement this ADT. Now, one abstract data type, one ADT, can have a lot of different implementations. Let's start with an ArrayList implementation. Class ArrayList stack implements StringStack. And what we're going to be able to then do is create a private array list of strings in here. And since we're bringing in the array list, we're going to need to import java.util.ArrayList. And I'm going to actually just move this out of the way and pull this down a little like this. All right, and let's make our constructor. And our constructor makes a new array list of strings. Whoops, there we go. And now, as we know, since we are implementing StringStack, we will have to implement each of these methods. Each of these need to be public because we cannot lose the same level of visibility as we had as part of our interface. And then rather than having these, these semicolons, we will go ahead and just start creating method bodies here. All right. So how exactly are we going to implement each of these? Well, a push should be adding stuff to the top of our list. Because we're implementing this with an array list, it makes a lot more sense to implement it always adding to the back of the list, list.add an item, so that we're not constantly shifting everything over, right? We don't want to always be shifting things over. Back of list is going to be equal to the top of the stack. It just will make it faster than if we were always working with the front because of the way array lists work under the hood. I'm actually going to jump down and look at these two now, since we will need is empty to go and do peek and pop. So in order to do is empty, it's actually really easy. We can just return if list.size is 0, because if it is, it's empty. And of course, this one is incredibly easy as well. We can just say return list.size. Now, when we look at these two here, we can ask ourselves if our list is empty. Whoops. If our list is empty. Because if our list is empty, we need to say list is empty. Nothing to peek at. We can make a string, peek, and it can start as null or an empty string, some kind of impossible value. And then we can always say else peek is equal to list.get. And as we know, we want to get that last element. There we go. And now we can return that, because a reminder, end of list equals top of stack. When it comes to our pop, we probably want to do something very, very similar, except our pop is not a peek. So this becomes a pop, nothing to pop off. This becomes a pop, this becomes a pop, and instead of a get, we would like to remove that last element. But otherwise, that code is mighty similar to each other. We now have one concrete data structure that satisfies the StringStack ADT. The outside world only sees the interface, as I will use in just a second when the main starts to play with this code. Inside the class, we're choosing to use an array list to store our stack information. We also could imagine a linked string stack that would use nodes instead of array lists. That would be a different data structure, but the same abstract data type. Let's go and look at how a client might use the stack. Let's head over to our main. We know that we need some kind of string stack because that's our ADT. And as we now know, we have one implementation of it right now. We can call that constructor, and now we can use it exactly as we'd expect. We can push the first element on. We can push the second element on. We can pop that element off and print it out, see what the heck is coming back. We can even check and see at that point what the size is of our stack. Let's go ahead and compile and run this so that we can make sure that it works as intended. As we know, I constantly make small mistakes, compile time errors, all sorts of stuff. So let's go ahead and take a look. Wow, none at all? That's impressive. All right, there we go. We can see we pushed first and second on. When we called pop, we got second back, which left us with only first on our stack, and we do now have a size of 1. That worked beautifully. We can even make sure that originally we had a size of 2. We did a pop, and then we got 1 back. There we go. Awesome. So our implementation works. Let's now go ahead and swap this out for a different implementation. We have our string stack. We have our array list stack. Let's go ahead and make a stack, a linked stack, I guess we'll call it. Linked stack. Implement string stack. So internally here, we can make that node class, private class node, that will hold our data and will hold our, node next. Awesome. 2 pieces of data as we need them. Let's just close that up and get it out of our way for a minute. And now we understand that our link stack should have access to a top variable, a private node top. Let's make our constructor. And as we know, that should set it to null. We're going to need all of those same methods that we had previously. We just have to implement them a little differently now. Whoa. There we go. Let's go ahead and grab those, plop them down over here. And now instead of a push like this, we understand that top needs to be a new node with, just kidding, node push needs to be a new node. Push.data needs to be the item. Push.next needs to be top. And top is equal to push. The order here matters. This allows us to reassign top to keep putting new pancakes on the top of our stack, putting new strings on the top of our stack. I could have made a constructor here to sort of avoid what I just had to write. I could have done node string data node next. This dot data is data. This dot next is next. And then it looks a bit more like my previous examples, where instead of writing all this, I would have just written top is equal to a new node with the item and the old top. So yeah, that's a little bit cleaner. Whoops, a little bit cleaner, obviously. Now, just like before, I wrote my push and peek, I went and I dealt with my is empty and my size. The best way to deal with size when we're dealing with linked lists, as we know, is to actually just keep a size variable. Since there's no easy way for us to just get the size like there is with an array list, we should just keep a size variable and return it, which means is empty just checks if size is 0. So that's usually pretty easy. We just can't forget that inside push, we need to increment our size. Now, within our pop, of course, we can now go ahead and check to see if it's empty. If it's empty, we can do the same thing that we did before. Empty. I'll even use the same error message. List is, I put the word list here, but I probably should have put the word stack. I'm going to change that up. There we go. So we can do the exact same thing. Right here, we can say stack is empty, nothing to pop off. Else, string pop equals null. Else, pop is going to be equal to top.data. Top needs to be equal to top.next so that we move it along. And don't forget to decrement your size. And of course, return pop. So now we have a pop function that is very similar to the ArrayList stack pop function in terms of what it does, but our underlying implementation is very different. We may not see a huge difference in efficiency when it comes to our pop, but we actually do see a huge difference in efficiency when it comes to our push. Because when we're pushing onto an array list, some copying may need to happen, right? We may need to double the length of the internal array for the array list, copy all of our elements over, things like that. We may see wasted space, right? We can see a memory difference. But when we look at our push and pop with our linked list, we're only ever taking up as much space as we need thanks to those nodes. Our peak, of course, looks very similar to our pop, just without that actual removal. So these two lines don't need to be there. Nothing to peek at. And I just changed the name of the variable just to make it consistent. All right, let's just add to our calls here. Pop and pop so that we can see what the heck is happening. So here we're still using our ArrayList stack, but now we can see 2, second, 1. When we do our pop, our next pop after popping off second, we're going to pop off first. Then when we try to do a third pop, we're told that the stack is empty, there's nothing to pop off, and we get null. So that's perfect, what we expect. What will happen now when I change ArrayList stack to now say our linked stack? Well, actually, I don't even want to clear it. I'm just going to make this a little bit bigger so that we can see it. I still need to recompile, but what do we hope to see? We hope to see the exact same output as before. Nothing should change from the user's perspective, even though our underlying data structure has now changed. Let's take a look and see if that's what happened. 2 from the array list, 2 from the linked. 2 second from the array list, second from the linked. 1 and 1, first and first, stack is empty, null and null. Even though we changed our implementation by changing the word array list stack to our linked stack, what the user actually sees and interacts with has not changed at all. And that's incredibly powerful and important. This separation between our abstract data type and our data structure will give us massive flexibility. We can change how we store things later on without having to rewrite massive parts of our code. And this can be important, especially as our needs for our applications change, or perhaps the storage and requirements change for our application. Next, it helps with testability. You'll learn more about this in future courses, but you can plug in fake datas or simple implementations of behaviors using interfaces to make our testing a lot easier and reliable. It also means we end up with much cleaner APIs. Other codes that will depend on the contract of our code. They depend on StringStack. They do not depend on our storage choice of a node or an array list. And that's huge. It also forces us to think about behavior first and implementation second. This is a huge mindset shift in data structures and algorithms, and will serve you well as you continue on as a developer or in some kind of software engineering capacity. So today we used interfaces to represent an abstract data type like a string stack, and we implemented it with 2 different concrete classes. We made an array list of strings and our linked node structure of strings. And we can see how we can swap one implementation for another without having to change our client code at all. So an interface is like an abstract data type, and our concrete classes is our data structures. In the next video, we'll get more practice by implementing interfaces with different backings and using them in more code scenarios. Thanks everyone, and I'll see you in the next video.